Hello, you're welcome to this lesson. So in this lesson, you will learn about series arrangement of resistors. So when you see a resistor, what is a resistor? A resistor is an electronic device that regulates the flow of current in an electronic circuit. That's what a resistor is. And what I have here is the symbol of a resistor. Okay, so you are going to use this symbol as the symbol of resistor in this circuit here. Okay, so when you look at these two circuits that I have on the screen here, I have one circuit here and I have one circuit here. You see that you have resistors in these two circuits, but you see that they have been arranged in different forms. So what you have on top here is known as the parallel arrangement of resistors, and then what you have down here is the series arrangement of resistors. In this video, I'm going to focus on series arrangement or series connection of what? Resistors. So looking at these two circuit, you are going to talk mainly about the second circuit I have here, which has resistors connected in series. So let's talk more about this circuit. So what are some of the properties of series connection of resistors? Okay, so one of the properties is that when resistors are connected in series, there is no node in the circuit. So you can see clearly here in these two circuits that with the first circuit you have a node here, which is this junction here. Okay, so when current is flowing from the power source on this direction, there are small yellow squares moving in these circuits indicate the flow of current. So when the current is moving from the source and then it gets to this junction, you see that what it gets splitted at this point. So we call this point the junction. So what happens is that electrical power coming from the source will be splitted, and then some will flow through this resistor and some will also flow through this resistor. By looking at this circuit, there is no node in this circuit. So that's one property of resistors in series. And also another property is that the same current flows across each of the resistors. So looking at this circuit, the current from the source, which is 1.389 ampere in this circuit, the same current that will flow through any of the resistors in the circuit here. That's another property, because the current doesn't get separated by any junction, so the same current that will flow across each of the resistor. And also another property is that the potential difference from the source, when the power source is distributed among the resistors. So in this case, this voltage from the source will be distributed among the resistors here. So there will be a voltage drop across the 3 ohms resistor, there will be a voltage drop across the 10 ohms resistor, and then there will be a voltage drop across the 5 ohms resistor. And what happens here is that the resistor with the highest resistance has the highest voltage drop. So at the end, when you add the voltage drops on each of the resistors here, it should give you the value of what the total voltage from the voltage source. And also one property is that the equivalent resistance is always more than the resistance of what any of the values of resistance for the resistors in the circuit. So when you calculate for the equivalent resistance in this circuit, the value you get should be greater than any of the resistance value for any of the resistors here in the circuit. So let's take some examples to explain the properties further. So first of all, we know that there is no node in the series connection, and also the same current flows across each of the resistors. So in this case, you see that I've named the current in the resistors by I1, I2, and then I3. So you see that they all have the same current values. And you know, current is measured in what? Amperes. And resistance is also measured in what? Ohms. Okay. So the first property that I talked about, you know, the current flowing in the circuit is the same across each of the resistors. So you see that what? I1 equals I2, and then I2 equals what? I3, and then they are all equal to 1.389 amperes. Okay, so that's the current in each of the resistors. And I also said that the potential difference is distributed across the resistors. So let's look at that. And we said that when you sum all the voltage drops on each of the resistors, it should be equal to the total voltage from the source. So let's calculate for the voltage drop across each of the resistors. And you're going to do this by applying Ohm's law, which is that voltage equals the product of what current and then resistance. In this case, you know the current for each of the resistors and then you know the resistance. So I'm just going to calculate for the voltage drop. So the first voltage drop will be equal to 1.389 ampere times 3 ohms, and this will give me a value of 4.167 volts. And then the second voltage drop will be equal to 1.389 times 10 ohms. This will be equal to 13.89 volts. And then the third voltage drop will be equal to 1.389 times 5 ohms, and this will be equal to 6.945 volts. 6.945 volts. So when you sum up all these voltage drops, it should be equal to 25.002 volts. So that tells you that the voltage from the power source was distributed among the resistors. And also one thing we talk about is how to find the equivalent resistance for resistors in series. So to calculate for the equivalent resistance, you just have to sum the resistance value of each of the resistors in the circuit. So the general formula will be R sub T, which is the total resistance, will be equal to R1 plus R2 plus R3 and so on. Okay, till the last resistance. Okay, so in this case, if you want to calculate for the equivalent resistance, that will be RT will be equal to 3 ohms plus 10 ohms plus 5 ohms. That will give us 18 ohms. So this will be the equivalent resistance, and you see that it is greater than any of the resistance value in the circuit. So the 18 is greater than the 3, greater than the 10, then greater than the 5. So that tells us that the equivalent resistance is more than the resistance value of what any of the resistors. Okay, so one thing you should know is that for series arrangement of resistors, anytime one of the component is removed or is damaged, the circuit wouldn't function. So let's look at this. So in this series connection, if I take out one of the resistors, you see that the circuit stops to work because of the open circuit here. But when you bring it back, it will begin to work. So that's one thing you should know about series connection. But as for parallel, if we take out one component, the circuit will still function. So you see that current is still flowing in this circuit here. Same way, if you connect light bulbs in a series form and then one of the bulbs get damaged or one of the bulbs is removed, the circuit wouldn't function. So this symbol I have here is the symbol for a lamp. So I'm going to take one out and then let's see what will happen. So when I take one out, you see that the current stops flowing in the circuit. Okay, that means that there has been an opening point here, so to prevent the current from flowing from the positive side to the negative side. So that's one thing you should know about series arrangement of what resistors or elements in a circuit. So that's all for this video. In my next video, you will learn about parallel arrangement of resistors in a circuit. Thank you.